Any questions so far? Any other questions? No? Okay. So if you have no questions, Brandon, you can start.
Sure. Just need to enable screen sharing so I can show.
You are the co-host, so you can actually do it.
Dr. Fu, I
Yes.
believe you made me co-host.
Oh, I mean, you co-host. Okay. Okay. Now, Brandon is a co-host.
Perfect. Excellent. All right. Can everybody see this?
Yep.
Okay, perfect. So first off, I just want this to kind of run like how Dr. Fu generally runs it too. If you have any questions or if you're just curious about anything, feel free to interrupt me as we go through. So I'm pretty much going to take you guys through the originating concept for this board, which was Brian Pearson's original concept to pretty much integrate security or cybersecurity with a crypto authentication chip on board a regular kind of IoT thing to convey data to a web server securely. So we're going to go through this entire process. It's kind of a lot to get through, but I feel like after this, you guys probably will be able to go on and design your own PCB. I picked a pretty straightforward editor for it too. So let's get going. So the original concept for this all works the same way. So if we want any board, you have a task to be done, job to be done, you might need a number of modules. So we have the actual dev board, whatever microcontroller that you might use, and then sensors or peripherals that you're trying to implement. So in the case of our board, there's a DHT22, temperature and humidity, a regular sensor, an output LCD, and the authentication chip. So this is a very simplified schematic of how to pretty much connect all of these as a breakout board. Now, the difference really between the breakout board and the module is the module right here is embedded on the breakout, and the breakout is offering all the peripherals, USB to UART converters, a couple of switching circuits, power regulation, all that good stuff. Another thing, kind of a side note here, there's you see these ADC and these touch sensors and all of these GPIOs. Well, on the ESP32, it's pretty nice. You can set these to either digital IO or analog. So if you're trying to read a continuous fluctuating signal, you can tell your program to read it as a continuous fluctuating signal instead of an on-off, which you can also do complete on-off. And you might use that for buttons or interrupts, but I'll get into that later. So what we actually need to do this is a schematic, but a more detailed one than the one that we showed before. Now, the schematic is going to be composed of symbols. So you see here, this is a integrated circuit or IC, a couple of peripheral capacitors and a couple of peripheral resistors. And all this circuit does is gives us a square wave. So this is just a standing oscillator. So these little squigglies here are your symbols, and they will each have a corresponding footprint. So the 5.5 A stable right here, the regular symbol for it, and at least in the editor that we're going to be using, is seen right here, and you can kind of see that it has corresponding pins. I have a better one for later though. So each component that we're going to use is going to have these two elements. There's going to be a symbol to it and a footprint. The symbols are just for the schematic. The footprints are going to give us an actual outline of what the physical component is, and that's what we're going to work with to do our PCB. So once we have all of these and our schematic is done, we can then go on to make something like this, which is just a PCB built around this circuit. But you do need all three of these elements to do any PCB. So elements of a schematic, we have, as I just said, the symbols, labels, and nets. This is one of the most crucial things. This is one of the things that I would mess up when I was first learning this as well, not naming the nets. So what a net is a single green line. Essentially, that's it. So if you look at this line from resistor 4 or R4 down to this little label here, all of these green lines and every red dot is all one connection. Every single one of these, as long as it's connected and not separated by some component or ground connection or some terminating element, is going to be all part of the same net. So this whole green line here and each of the ones that come off of it is all one net. And that will have a net name. It's usually given to you by the editor. As you draw it out, the editor will assign it a net name. So ground, it defaults to GND. Something like this, it might default to like a R4, R3, something like that. But you got to make sure your nets are okay. Because if you have so actually, for example, this little tag here that says V0, this is our output voltage. And you see that in a couple of different places. Well, if I put one of these V0s on this net, your program is going to break. It's not going to know what's going on because you gave a net 2 names. So it won't be able to make any sense of it. The other important thing is trying to do this as cleanly as you can. You want clean schematics. I'm going to show you guys a really, really ugly schematic later from the 90s. And I mean, I'm only an electrical engineer and I can't make sense of it without a ton of scrutiny. So you want to do isolated design. So these are all still connected to one another, but they're in strips here. There's no peripheral lines coming off of this. We're using net labels to make this happen. Let's see. Yeah, it's about all of that. Any questions about what's going on here? Does this all make sense?
I have a question.
Yes, sir.
So the USB con micro, the schematic all the way to the left, like where does that correspond to the board that you gave us?
So where that would correspond is I actually use the same exact connector. I have mine plugged into a case, but it's the USB input. I popped mine into this case and I didn't tolerance it too well. It is this component right here, the USB bit. So actually, as you can see here, the SH1, SH2, SH3, those all are actually corresponding to like these little side terminals that are actually connected to the board. That's why I just plugged them all to ground. The 5 pins coming off of that are these 5 pins right here. This is pretty common for a micro USB to just use the same pinout, but for any USB connection, you're going to have a plus, a minus, and then a data plus, a data minus, and sometimes there's an ID if there's an actual set specific device that you need to communicate with, but you generally don't need it for simple applications. But yeah, so this symbol corresponds to this exact connector. So there are a bunch of different USB connectors. Some of them are a little bit longer. If you'll notice when you plug this in, not the entire strip goes in. There's a little bit hanging out. That's just because this is the one I picked. You can pick connectors that have deeper plugins. You can choose to really do whatever you want. You could even turn the SH5s and 6 into your power terminals. It's just not too advised. But so this symbol, the USB symbol, has the corresponding footprint for this. So once I associate all of these components with each other, the editor that I'm using will automatically go and grab the footprints for these. So that way, when I convert this schematic into a PCB, it's doing it all for me. It's going to make sure each footprint is exactly the component that I picked in real life. Does that answer your question?
Yeah. So for each little piece on the board, you have to like solder it onto there, right?
Luckily, no. So for wherever you order from, they'll have different policies. A lot of places won't put on connectors for you like the USBs. So I soldered every single one of the USB connectors on your boards. But the stuff I didn't need to solder are a lot of the small units. Anything with R or C, I didn't solder. U1, I didn't solder. And all the diodes and whatnot, anything marked or denoted with D, But if it's bigger, like the buttons, the pin headers, the LCD, I put a lot of that on. That it's a little bit simpler to solder something that's, we call it DIP, which is through hole. And a through hole component is going to be like this LCD, how there's an actual physical hole that permeates all the way through the board. Makes it a lot easier to solder than something like this little chip right here, U3. There's no holes there. That's what's called SMD, or surface mount. And it's a little trickier to solder because everything gets very, very small. So you kind of have to weigh out what you want to solder and what you want to, what you want to avoid. It's also really important to consider in component placement, but we'll get into that in a little bit. So go ahead if there's anything else.
Brendan, I heard from Clayton. Clayton said, not Clayton, from Halfway, and he said for the other board we actually made, and you can actually order the soldering service. And that's what they said. So basically, for example, if we want to solder that USB collector onto our PCB, we can also order the soldering service for that. Is that right?
It all depends on where you order from.
Okay.
So for these boards, I picked a very simple editor. It's the same very simple editor that I'll be showing you guys today because it makes ordering and assembly very, very simple. They have a couple of parameters, like they don't solder on the ESP32s, any connectors, but really anywhere you go is going to have some sort of guideline like that, where they won't do this, they won't do that. I forget where Clayton ordered the other ones from, but I think they did our connectors. This is a much simpler board. It wasn't too much to solder them on, so I opted to go with these guys. They make ordering very simple, and we'll also get into how to actually order and make sure everything is good to go, because you have to have all your files in a very specific way for them to just take it in, read it, and give it back to you assembled. But yes, you're right. Most places do have an assembly service, and we use that for these, just minus the larger components, effectively.
Okay.
So again, yeah, a little bit more about the symbols. So whenever you pick a symbol, and we'll get into what the libraries are, but whenever you go to an ECAD editor or a program that you make schematics and PCBs in, they have a library. So they're going to have a enormous list of components that come in all shapes, sizes, packages that already have their set symbols and footprints already associated with them. So that's the case here. So say we're doing this simple oscillator. This uses a 555 IC. It's one of the most basic op amps out there. It's actually technically not an op amp, but it's a very basic IC. They're used everywhere. So we can go right into our editor and get this symbol. Once in a while, you'll have a component that doesn't have a symbol, and you can create symbols and footprints, but most of the time you just simply don't need to do that. You have to be using some really obscure components to have to do that yourself. So this guy is going to correspond directly to this. So as we give this to our program, we have each of our pins already configured. And if you look on the actual diagram for that symbol or that component, you'll see that 8 is still VCC, 4 is still reset, 3 is your output, and everything is correspondent. So you don't need to line up the shape or the side. You can just start connecting nets. And again, all of this stuff is just representing the actual physical package that you will get soldered onto your board. So that's about all there is to symbols, actually. Yeah, there's not too much form, except that these pins each have an associated net. So the pin name right here is not the net name. It'll be part of the net name, but again, the net name is going to be the interconnect in between components. So if you had a line, say, drawn from 3 to 5, that the line in between 3 to 5 may be called out/cont or something, because it's using the pin names to create the net name automatically. But those are two separate things. So Each symbol has a corresponding footprint, and this is the corresponding footprint to one of the packages for the last chip that we looked at. So this is also what I mean by packages. Stuff comes in an array of sizes, and some of them for ICs are down here in the bottom left. So SOP is like the U3 package on everybody's board, but they get smaller, they get bigger. There's all different kinds. So even for this same footprint, there's another footprint that's slightly smaller. That's the exact same chip. And then the same goes for capacitors, resistors. So any R1, R2, C1, C2, all those things. These all have a metric code for them. So most of the components on our board are 0603. And you can actually see that on this handy little tool. This gives you the sizes here. So we are all the way down at 0603, which is very, very, very small components. They do get smaller, but these are quite small. So these are things that you would just pick your preference. It's not always preference. There are certain parameters, like if you have a resistor that's safe for power management and it's going to be dealing with a lot of voltage and current, you are probably going to have to use a larger package because you physically need more, not resistance, but tolerance, that it needs to be able to take a lot more punishment than a physically tinier resistor. Because with enough current, every resistor is going to act like a fuse. Eventually, they will explode. So size does matter. That said, for the very small oscillating board that I showed earlier, you wouldn't need any of that. You can go 04, 02, completely tiny components, just again, to make it very small. So on this, we can use 0603 because we don't have a huge component density, but on a Raspberry Pi or something like that, you're going to see a lot of 04, 02 components, which are, I mean, barely visible. But yeah, so your component size is really gonna be dictated by a couple of parameters, which is just the overall size of your PCB, any constraints that have to do with just the dimensions of that. And then again, power in some cases, but in general, 0603 can handle anything up to about 10 volts. After that, you might want to go to something a little bit higher if you're dealing with anything over 12. But a 9-volt battery is totally fine to hook up to a 603. Any questions about this? Oh, actually, one more thing. See this yellow outline here? This is a silkscreen layer. So this is going to get printed on the outside of your board. It's not conductive. It's just there to show you how to position the IC, because when you get these, they're very, very, very small. So you see this little circle in the bottom left, that marks pin 1 on any IC. If you ever see the little circle in the top left, that's pin number 1. Yeah, that's all that's really there for. The pads, the red here, these are copper. That's what you're actually going to physically solder to. But yeah, apart from that, those are footprints. You can edit these yourself, again, for specific components. You usually don't have to. And I'll show you a couple of different examples of different footprints going forward. So we have our key components that we needed for this project specifically. So the crypto authentication chip, the ESP32, the LCD, and the DHT22. So in order to get all of these bare, naked components to talk to one another, they're each going to need some sort of peripheral circuitry. Luckily, you don't actually have to know a ton about hardware to be able to do this because they have data sheets. So this data sheet here isn't really going to reveal a lot of peripherals since this is sort of a standalone device, but this is a couple of things off of the actual data sheet. It'll show you what every pin means. So this is using the I2C bus, which is just a data bus communication. It's a 2-wire bus. One is for data, the other one is for clock. They work in tandem. There are plenty of libraries out there for a lot of I2C devices. They're generally preferred and very easy to use. But yeah, so this will correspond to the pinout. you can double check that the voltages on your board aren't going to kill this thing. So on our board, for example, we had 5 volts and 3.3 volts. So I had to decide which one to hook this up to. So this involves me going to the data sheet and checking out what its VCC is. So being 2 and 5, I picked a 3.3 volt instead of the 5, because why waste the voltage if it'll run on 3.3? So also in the bottom left, you'll see 2 different packages that this comes in. So one, the package on the far left, the SOIC, this is the package that we ended up using. This one's a lot larger than the package to the right. Now, the only reason I went with the larger package is because they ran out of the other ones. So that turned into a very lengthy soldering job. But yeah, so these are generally just things that you might need to look at. This is generally overkill. Ideally, you want to go to the data sheet, know what you're looking for, such as how much should I power this thing with? And you can generally have a pretty easy time just finding what you need for that. So this guy didn't need much. There are 2 pull-up resistors on there. I don't plan on getting into pull-up resistors today. It's just a means of securing data communication and holding the voltage at a certain place to make it readable. So there are 2 external resistors that are paired with this guy, but it's not mentioned on the data sheet, so I'm not going to open that up. DHT22 is same sort of deal. We needed a slightly higher power supply. 3.3 was on the low side, so this guy's powered with 5 volts. Single wire bus. This is just a different form of communication. Generally, you can just search it, go online, DHT22 hookup, and you just start reading about it. It'll generally show you how people have hooked it up before. But this is pretty simple. We have voltage, data, and ground. Anytime you have data, you're generally going to have a pull-up resistor. But that just kind of comes from, practice, experience. It's a good rule of thumb to just have a 10K inline VCC to data. It's essentially implied by having any data pin. The tricky one, though, is the LCD, because this does not use a conventional protocol to communicate with. They sell these with adapter boards that use I2C, but they don't come out of the box by themselves, ready to use it. So these actually use a very long series of registers. So on the right, you'll see at the very top, these are the values that are being plugged into each register and the corresponding bits on each column. So to actually control this LCD takes a ton of background programming, and there's a bunch of there's a single library that has many sub-libraries in it that's used to crunch all this data. So you can go into your IDE and go, LCD.write and just send it a string and it'll actually just print it. But there's a lot going on in the background of this, which is why there are some preferences for other screen types, like an OLED uses I2C. That's only 2 pins. TFT screen, which is another LCD, but it's much smaller. It's actually this is a TFT. It's a lot higher detail. It does full color, and you can go all XY. So you can turn this little LCD into something like an oscilloscope, where this is just kind of a bitmap. So, oh yeah, we can. We'll open the data sheet for the ESP32, because this is really the guy that matters. So this again is just the naked module. So you generally always want to go to the data sheet of such things. And in here, what I'm looking for right now would just be the peripheral circuitry that's recommended by the company. And here it'll also show me the pinout. And it does a great job of summing up what each of these pins do. 2 major pins here is enable and IO0, but we'll get into that a little bit later as well. It's called strapping pins. Yeah, we'll get to that. But right now we're going for there we go, peripheral schematics. So I just wanted to show you guys that these are available on any data
Brandon,
sheet.
can you make your screen a little bit bigger? Can you make your PDF a little bit bigger?
Oh, it's small. Sorry, I'm on a
Yeah.
double wide.
Uh,
I have slides with that stuff in it. I just wanted to explain that you can go to the data sheet and pull that information.
okay.
So again, so we see our power supply here. It's a lot tighter. It's just 3.3 volts. So that means to power this guy up, because USB is going to give us 5, we absolutely need a voltage regulator on there. Luckily, they make those very, very easy to use as well, and they're also recommended in the data sheet. So this is the first schematic that we came across in the data sheet. This can be a little hard to make out. You don't really need to get into the nitty gritty of this. If you actually did this, you can save the PDF. And what I like to do is I'll actually take the image and impose it in my schematic editor. That way I can just reference the image as I make the schematic. So a couple of things that are going on here, all the way at the top, this U1, this is the internal crystal that's going to work as the ESP's clock. You'll see a lot of these little symbols right here, which are just capacitors to ground. These are really just to protect the circuit in case of a power surge or something like that. If they got over current or over voltaged for a moment, these help kind of eat some of that power and don't let it just dive into there. So all of this is already inside here. This is all under the hood. This big metal sheet contains all of this stuff. So the ESP32 module itself is its own PCB. There's all these components just sit right under there. And again, like I was explaining earlier, the schematics and net names, he's separated all of this so he doesn't have a bunch of lines spanning out in every direction. So this is just going to be a lot cleaner, a lot neater, and you can see the net names on each line denoted in red. The blue squares that he has are just raw pads. So they're going to organize these however they see fit, but it's describing these little half circles right here. And they each describe a pin on the ESP module. So once we have the module, this is the rest of the recommended circuitry that off the data sheet, at least. My recommendation is to look at a few data sheets and understand why stuff is there, because this is incomplete. This is off of their data sheet, but this does not tell you even remotely everything you need to support one of these. So looking at this, we see C1, C2, delimiting to ground. You can go on here and find those. They might be these guys. They're very, very, very small components. This is an important one, the enable pin. That's the enable button on there. And again, we'll get into that a little bit later about the bootstrapping pins and why that is there. But they are leaving out in the data sheet this chip and this power regulator and the USB connector. It's pretty much raw. This is just to support the chip. So what you'll want to do is go find the data sheet for the dev kit, the actual full board, if you were to reconstruct one of these. So things can be a little misleading. You definitely just want to make sure you're looking at the right thing, especially if you don't know what each of these individually is doing. Right, so this also is the footprint corresponding to this chip. This is how they come, and this is one of the useful ways I'll be able to actually see what I'm doing before I put this on, so I can make sure that I'm soldering it onto the board correctly. These are mostly self-explanatory because they don't have symmetrical pins, but this is very useful off of the data sheet. If you did need to construct this yourself, there is a footprint editor, and this shows you exactly how much tolerances things should have, their widths, their heights, and each little blue square here with these lines across it is a pad. So it's what you're going to solder one of these little copper pads onto. And yeah, actually that's generally all there is to that. Is there any questions up so far? Nope. Okay. Again, so this is dimensioning. So this is actually pretty important if you plan to have any kind of physical constraint or to make a case or housing for it. So I've had prints or I've had designs around PCBs not be able to be used because I did not leave enough tolerance in the back, because I did not know how tall certain components were. So if you do get into the 3D printing element of it, knowing the size of stuff is pretty important, especially when you're trying to design exactly what shape and size you want your PCB to be. You might have a chip selected and it could be a little bit too large for, you know, how small you're trying to make it. Oh, no, other way. So these are the bootstrapping pins. Now this is from the ESP32 datasheet, and this is why you have 2 buttons on your boards. There's a couple of different modes here, and again, not all of them are even listed on this datasheet. You'd have to go to the WA Rover datasheet to actually find them. But GPIO 0, SPI boot mode, download mode. So one mode is for flashing, the other one is for actually starting, booting, and running the program. Now you see GPIO 2 is don't care, that's fine. So as long as that's not pulled high for some reason. And when I say pull high, I mean there is a voltage on it that is above a certain threshold. On an ESP32, I believe that threshold is just about 1 volt. So you have a digital pin, which is what all of these guys are going to be. You can either have a 0 or a 1. Now, if you have 0.999 volts on a given digital pin, that will register as a 0. If it goes above that, that's going to, any bit above that, 1.02, it'll register as a 1. There is a threshold and it will be triggered immediately. You can't have anything in between. So this is how we control the mode or the state that our device is in. And again, this is a really important thing. With ESP32 specifically, there are plenty of other microcontrollers that don't require any sort of peripherals like this. They, what is it? The AT Mega 38 AU is pretty much a standalone chip that just doesn't need to be put in any sort of mode. You can pretty much just plug it in, program it, and start it, and it's good to go. This is also pretty important too, because with ESP32, there's actually an internal voltage regulator. And if this starts up and one of these bootstrapping pins is high, that shouldn't be, it's actually going to try to run the chip at 1.8 volts instead of 3.3, which is going to cause the chip to burn right out because you have 3.3 volts connected to it. So you really got to get to know the data sheet before you're able to actually manipulate these. The PCB that we're going to make in just a few minutes is, apart from this, it doesn't need all of that because it's a simple enough circuit. It doesn't have any sort of microcontroller on it. There's nothing that you can program. It's just a standalone circuit. Right, so we found that the data sheet for the ESP did not include the UART to USB converter. So knowing that we have a UART to USB converter on there, or just observing any other ESP32, you will see a chip on there called a CP2102 or 2103 or 4. There's a bunch of different kinds of them. But this is kind of where the peripheral circuitry starts to flow in. This U1 right here was not in our list of key components. It is not technically crucial to running the program. It's really only for ease of access as far as programming these go via USB cable. So this is what's going to enable that. So I hope you guys can see this. Is that good? It's kind of large.
Good.
Excellent. Yeah, we're going to speed this up. So again, we've got our dimensions for it, and that circle in the top left marking pin 1. Small enough, we don't care. Come on. Oh, there we go. So this is actually all the peripheral circuitry that you will need for this guy. Now, you'll read on to, it'll explain what each resistor is, what each capacitor value actually should be to do certain stuff. So it'll actually give you a couple of different schematics and offer pretty much whatever configuration that you need. This is an important one for that chip in particular, because if you power this with the 3 volt, this is like if you plugged in both of these at the same time, you're going to power the entire device with this chip. which you do not want to do. So you do kind of have to read through this, and it will explain that you don't want to actually do that, that this is explaining a kind of a one or the other. In this case, this is from VBus, and this is the output. This is powering 3 volts from VBus. It's essentially saying that there's an onboard power regulator, and if you give it 5 volts at VBus, you will get 3 volts out at VDD. Let's go back to the slides. No, where are we at? Right, so again, yeah, that's this voltage regulator. So this is the adapted schematic for what we just saw in the data sheet. A couple of capacitors, just a couple of VDD, don't let it get overloaded. And we are going to power this guy from the USB. So since we have an onboard power regulator, we don't need to tether anything here. We can just run this off of that. Again, this knowing to do this would come from partially reading that data sheet, not the whole thing. You never just open a data sheet and read it. Some of them are literally thousands of pages long. You generally open the data sheet, want to get an idea of what you're actually looking for, and then find that element, read about that element, and then go back and try it out. Yeah, so this is just an example of how your simple idea, because if you remember the original schematic that I showed you, we had 4 components on there. And now just for a part that wasn't even shown in that, we have 1, 2, 3, 4, 5, 6. So this is what? Oh, I'm not plugged in. Excuse me. There we go. So, right. So this is how your PCB ends up not looking like just 4 big things on here. That's why you end up with up to R11 and C12. It's every little device that you have on there generally has some kind of peripheral, and that's really what you go to the data sheet for. So this is just a little bit more about that chip, noting what capacitor values to do. So you can see here the VRAN, the VDD, and the V ground, and those are the same values that we'll have to adapt to ours. So picking the ECAD software. So now you know all of the devices that you need, the peripherals, and now you want to make your schematic. You have all the data sheets open. How do you pick an actual software? Luckily, I'm going to pick Force today, but you generally want to go for something that has very extensive libraries, so you're not creating components yourself. When I first started using Altium, I had no idea how to link libraries, so I was pretty much drawing symbols and footprints for absolutely every single thing that I was putting on that board, and you just don't want to do that. So we're going to use one called Easy EDA. It's online, or you can download the app. It's very nice. It does simplify the entire process. Now, it won't have every single exotic component that you need, but it does make ordering very, very simple, which it can be very difficult. You might download all the files that you need to order a PCB and have to actually open them up in other software and edit them. And they can be long. They can be very long because they're going to list absolutely every single component that you have on there. So you definitely want to pick a good editor. Personally, I like KiCad, Altium, and Easy EDA. Don't really recommend EagleCAD. Some people love it, but that's just me. But again, popularity is actually one of the most important things, believe it or not, because the more popular it is, the more footprints and schematic symbols people are just going to be adding to this constantly. So some CAD softwares they're a little bit more nichey, and therefore the libraries that you get are either from a certain manufacturer, which they might only make like this chip, that resistor, and this capacitor, or they'll have a few people out there that are actually designing and uploading components for it. So you generally want to pick one which is going to have extensive libraries. That way you're not wasting time in the component editor and drawing your own footprints and making your own symbols, because that's where you can absolutely make mistakes too. You have to get every pin and pad size right. So this is the very ugly schematic I was talking about. So this is from the 90s. And back in the 90s, they just didn't have the tools we have. So everything is literally just drawn as a line. And you'll have to sit there and follow each line to find out what it's connected to. This is actually a schematic out of a really old school monitor from the 90s that a buddy of mine was modding to do RGB, and we had to find the right connections in here and tether them to an ESP32 so we could control the coloration of the monitor with his phone. But this does not make things easy, especially if you designed this and then you want to go back and change it. Finding a specific component or knowing exactly what it's tethered to can be a nightmare if you don't organize your schematic in a way that is readable. It's like commenting throughout your code. It's you want somebody else to be able to look at your code and make sense of it, whereas this is just heinous. So this is a much prettier schematic. This was made by another student that was working on a project that we've been doing with Dr. Fu. It's an air purity project. And as you can see, he isolated everything. So here you don't have all of these wires tying everything in together. Everything is as isolated as it can be. We have power net names here, 3.3 volt, 3.3 volt, 3.3 volt, but we're not wasting space or we're just not making a mess. You can isolate any one of these and have it stand alone and it'll be just fine. It's just a much cleaner way to do it. And again, you don't want to edit a schematic that's just has a million lines drawn on it. Any questions about this or about the net names specifically? Nope. Good. Cool. So this is actually the schematic that we use. Now about the bootstrapping pins, again, that's what this switching circuit is for. This wasn't really off a data sheet. This kind of just had to be done. And here you can see kind of what this circuit's actually doing. It's pulling IO high when RTS is high or DRT is high. And this is just a means to let the USB tell the chip that it's about to open up, it's about to program it, and when it's done programming it, and when to go back to boot mode. But here I tried to isolate things as much as I could, stuff that doesn't really have to do with one another. So for example, IO33 to SCL, IO27 to SDA, those are connecting two different nets, right? It's connecting these two nets, SCL and SDA, which is clock and data, to two pins of, Brian originally designed this. I kept his pins, which are 33 and 27. Those are not the stock pins for I2C with ESP32, but you can reprogram ESP32 to assign any two pins for clock and data with I2C. But this is an example of just kind of how you want to organize something. I am a little OCD with it. I like to even draw lines throughout. Sometimes I'll label what exactly is going on in each quadrant and why it's there, and I'll add links and whatnot to get to where where I learned how to do a certain circuit like this. So to actually make a PCB, so we're going to be assuming that we already kind of have a schematic from this point on, but just a couple of considerations are going to be tolerances. This is going to be the proximity of components and nets. So you want things to be fairly spaced out. If they're too tight together, like if you see these two bus lines here, if these are closer together, you can actually get a little bit of spillover, especially if one of those lines is high, as in there's a higher voltage on it, and the other one is drawn low. This will create a capacitance. So you don't want that, because you'll actually get voltage leaks and bleeds, and sometimes you'll even get a connection where you very much do not want one, and nothing will work. Some of this stuff is also small enough where you are going to have a very hard time finding out where that connection is. if you're having problems and you manage to narrow down which component is actually messing up. Another thing to consider is the trace width. Now that's really important. So if you look here from D1 to C3, this is a much wider trace than the data lines. And the reason is that this is conducting power. So as I mentioned earlier, this is since this is a power line, you want a wider trace. You want the electrons to be able to spread out and not get clumped up together and start bumping into each other, because what you'd be doing is creating a resistance. And we just don't want that. So you want big fat lines for your power. There is a convention to it. In this case, since we're only doing 5 volts, I left them at 0.45 millimeters, which is plenty. But if we're going higher than that, or if especially if you're going to have a high current, you might need to expand those by kind of a lot. Now, the blue in the back, so anything that's blue here is showing the bottom layer of the PCB, and I'll be showing you guys what the layers actually are in the next slide. But this is a 2-layer PCB, and this enormous blue plane in the back and the one above it, these are voltage planes. So what this means is there's a big layer of copper back there that is all like 3.3 volts. It's all one giant trace. So these little holes here are what's called via, and that'll go down and connect this wire right here to that giant plane. So that's why you don't see wires all over the place. They're just going a little bit away from their component, and then they're getting via'd into the power plane that is beneath them. The ground plane is up top. I have it disabled right now to make this a little bit more readable. But to see that and visualize it right here, these two cylindrical shapes here, this is a via. So it'll take a trace, which is our connection, our actual copper trace, and it will connect it to a layer down beneath. So you might need to do this to get a line, under other lines that you already had. And I'll show you guys an example of that a little bit closer to the end, when I'm just going to give you an example of how to actually just make a PCB from a starting schematic. So this would be a 3-layer board in the sense that ground and power would also be planed out, right? So you do have your top layer. The middle's usually FR4. It's just plastic. It's generally, I think, 1.6 millimeters in height, and the reason it's so high is to prevent capacitance vertically. So if you have this top copper layer and this bottom copper layer as power and ground, and this substrate is too short, that is a capacitor. That is the definition of a capacitor, and it's not going to work. So you need at least X amount of distance in between here. Again, unless you're working with, a couple 100 volts, then you're generally fine with 1.6 millimeters. That's what they're going to recommend that you order stock anyways. So you can generally stick with that. A couple other things, the silk screen, what that's describing is the white lettering that you see off to the right. This is really just for, again, readability. So if you have your IoT kits in front of you, you can see the 2 LEDs in the top left corner if you're looking here, and you'll see power, PWR, and LED 2. I call this LED 2 for 2 reasons. 1, it's an LED, and 2, it's connected to pin number 2. That's it. But I wanted that to be readable, so that way I or y'all would forget that it is pin number 2 if I wanted to program it as such and declare that pin as that LED. So just beneath the silk screen, we have the solder mask. Solder mask is the layer of intrinsic material that's going to be put over the actual copper tracing. So that's why if you lay your hand flat on a live PCB that is conducting electricity, you will not get tased. It is for the reason of that solder mask. It's just a resistive layer that is not going to let electricity through, top and bottom. So this was a totally real-time video. I'm just that good at this. Kidding. But this is generally how you will want to lay out your components, or what it might look like in the actual editor. So a component placement is extremely important. I'll zoom in a few times, and if you can, I know it's super fast, but I wanted to show this quick. But you can see the little net names on each pad if I zoom in enough. And what I'm trying to do here is organize these in a way where they're far enough apart, but things of similar net name are close together. So if y'all recall when we were looking at the other schematics, how there were 2 capacitors in parallel going from both 3.3 volts to ground and 5 volts to ground, and even just the raw USB in to ground, you're going to want to put those next to each other. So this will, this doesn't go on for much longer, but oh, I guess it just stopped. Close enough. Okay. But yeah, just a couple of considerations. Making your silkscreen readable. I did not do this the first time, and it was a real pain to work with the PCB after and to kind of remember what component was what. So making this readable is pretty important. Just so I can reference, hey, everybody, look at U3 on your board. If I had put that U3, like the lettering, if I put that in the middle of the footprint, for example, you would never be able to see it. So you wouldn't know what I was referencing. It's also very important for certain things like your pinout on the headers. All of that stuff is the silk screen, the labels for each pin, all of that's on the silk screen. So you just generally want to be mindful to make that readable and try to organize it as you can. But as far as component placement goes, you generally just want to try to make sensible decisions. If you have, say, two components that are tethered to the same pad, you're going to want to put them closer together. So that way you don't have an extraordinarily long trace going across your PCB. Reason you don't want long traces also is because they will eventually, they are resistive. Copper does have a bit of resistance, and the longer it is, the more resistive it is. So it's more like putting a resistor where you don't want one with a very, very long trace. So once we have our components all in place and we're happy with our placement, we can get to routing, which I think is the fun part. Again, totally real-time video. So,
excuse me.
Yeah, go ahead.
How long did this take you to design and implement?
So the first board, the ESP32, the first one that we did for this class, took me I don't know, maybe like a week to design it. And I had some problems with it. We ordered it and it just didn't work at first. And I found that I had gotten a couple of pins wrong on the USB to UART chip. So I had to actually solder in tiny little connections just to make sure that it worked. And after I'd fixed it, then that tells me how to fix the next one. So I go, okay, I had to change this to make that happen. So I just go change that in the schematic, and it's essentially done. Now, isolating what the problem is, that can be tricky. We're going to get to that at the end with some testing. But isolating the problem for such a simple kind of PCB it's not too bad. But it's all relative to the general complexity of the board that you're doing. Like if you have a really simple board and has a power LED on it, and you plug it in and the LED isn't on, it's okay. You're probably not getting power. Like something's not connected. But yeah, it took, I think, about a week to just design it the first time. But the first time I designed it, it did not just work. So after fixing or correcting everything wrong with that board, and then reordering and then testing the new ones, probably about a month and a half altogether. Now, that's not the case with everything. I'd actually had a hard time with ESP32s in the past and like their boot modes and stuff. So really just what it took was really just getting familiar with the data sheet and just familiarizing myself with the parts that we were using. Other stuff is a lot quicker. Actually, so and not only that, but once you actually have this, once I had a functioning ESP32 schematic, then I can just drag it and drop it in another schematic to make it work with other stuff. So you can kind of save that one schematic and then just add to it if you like. So I can show you guys another board that I recently designed that's a lot more complex. It's a JTAG debugger with an ESP32 on board, and that one looks a lot crazier than the one that we got. It's a little bit more expensive, and the complexity again is through the roof, but it was made easier by already having an ESP32 and all the peripherals already done. So you can really build on what you already have. And then it will give you a nice 3D model. But does that answer your question?
Yeah.
So yeah, again, just a couple of considerations. It's just the trace width. 0.254 millimeters is a industry standard for both pin width. So 2 pins, like the header here. If you put in 2 random pins in here and then measure the distance in between the very center of those pins, it's going to be exactly 2.54 millimeters. The other couple things to consider is minimizing vias where they're not necessary. That said, vias can be really important for a number of reasons. It's not just the connections that you use them for. Under each of the ICs on this guy, for example, under U1 and under the ESP32 and U2, the power regulator, there are a cluster of vias put together, and those are just there to absorb any heat that's going to be produced. When you have small ICs and they're conducting power and they're doing their job and they're thinking about stuff and moving everything around, they're generally going to heat up. Especially power regulators or any MOSFETs are always prone to heat. So if you have something that you know is going to warm up a little bit, it's generally a good idea to throw some vias under it, not close to any pads, just to kind of have a built-in heat sink, if that makes sense. The other thing is you don't want 90-degree angles. Electrons move very fast, and they're already pretty cramped together. Imagine like you're in a crowd, and like a big crowd, and you guys are all sprinting as fast as you possibly can through a hallway, and then all of a sudden that hallway takes a 90-degree turn. You guys are going to smash into that wall and into each other. But if it just curves off at about a 30-degree angle, you can generally make the correction, and only a couple people might get flung off to the side. But that's generally why you don't want 90-degree angles in your routes and widths, if that makes sense. So ordering, I'm going to show you guys an example of this in just a minute, but these are 2 of the 3 pretty large files that you need for ordering. So the first one is a BOM, and this is just a list of every single component that's going on there. So for these boards, we are ordering from LCSC, and we got the assembly from LCSC too. So here you can, a little bit cut off, but it'll tell me like which components will be assembled and which ones won't be. You can see all the footprint, the 3rd column in footprints are all filled up so that it knows exactly what pads to put on my board, so I won't have a hard time soldering. It knows how many of each thing that I need, has its supplier numbers and its price. So if I see something crazy on here, like this $7 price here, that's kind of alarming. That might make me that might cause me to go back and see if I can do the same thing for cheaper, because these do rack up. Except, wow, some of these are under a cent. That's pretty great. The other is a pick and place drill file pads and holes. So pads and holes are pretty much any actual physical hole that you add to your PCB. So these holes right here are just for general purpose. If you put this on stilts, or if I CAD a housing for it, I want to be able to generally secure it in some type of way. This will involve me putting a screw through it. So I just had a couple of holes in there just to make that easier. Apart from that, this file right here, the pick and place, is going to describe absolutely every single pad. So as I was saying earlier, we have our component footprint sizes, and that's what it's actually describing. So it'll have, so we see C3 right at the top here, how it's a 0402, that's an extraordinarily small component. And you can see that the ref 9 is to pad 9. The difference here is how big that's going to be. So it's like just over a millimeter. Very, very, very small. But this file will allow them to pretty much just put your design into a machine, put some FR4, which is the plastic material substrate. It's not really plastic, but it's what they use in PCBs. It'll allow them to put that in their machines, and their machine will tool and etch on every single pad at exactly the way that the footprints dictate it will go. So this file works with this file. This one describes those footprints. These footprints are then translated into these drill paths, and then they can pretty much just feed this exact file into their machine, and it will know the corresponding component, where to put it, how to orient it, and how much copper to lay down. Any questions about this? Because this is one of the things I had a hard time with when I was first learning this. What's that?
Brandon,
Yes, sir.
what was the last column in the BOM?
And the BOM is LCSC assembly. This is just telling you which components they will assemble and which ones they won't. So up at the top, you see item number 2, they will not solder on a DHT22. It's a DIP component. It's very large. It's just not one of the ones that they're going to do. Connectors, large components like that, it's not really their bid. So they won't solder that one. Now the one above it, you can see is an LED 0603. This design has other LED 0603 package sizes, but they will not assemble this one. Now, that's generally something you'll want to go fix. You don't want to solder an 0603. So vetting these are pretty important. And in here we can see we have actually a couple of them that they will not assemble. So this would cause me to go back into my schematic and check out a number of other symbols to replace those LEDs with, and then resubmit and see if they will then assemble those ones. So they'll assemble some buttons, certain stuff. You really just have to look into it and see what they're up for, and what they have in stock and what they're willing to go out and pretty much order for you. But was that the column you were asking about, the assembly?
Yeah, so sometimes you can just reassemble components, and that will change it.
Yeah. Some of them, like this manufacturer, I've noticed they don't really mess with. Just don't get. They just don't pick up components from them. So just changing the manufacturer, because this LED, there's thousands of these out there, by tons of different manufacturers. So just to get an LED of the same size and color wouldn't be too much of a challenge. You just go back in your editor and grab it, switch it out.
Okay, thank you.
Of course. So then the big one is the Gerber file. Now, or Gerber files, pretty much what each one of these is doing is it's describing a different layer. Now, even on a 2-layer board, you're going to have at least all 6 of these. You will have a top copper. That's all of your pads, all of your connections, pretty much any tracing, your routing, your widths, all that stuff. You'll also have bottom copper. If you do have a 2-sided board, we did have a little bit of bottom copper on this because we had through-hole components. So it's just an entire large size via, essentially, that goes through there. So you do have copper on both sides. In between, again, that's FR4, and then you do have your top and bottom solder masks, and then your silk layers. Now, the silk layer is, again, the writing. People do artwork on them. Some PCB manufacturers will actually allow you to do extensive, detailed artwork on there, and they'll let you pick your colors and whatnot for, to really customize your board. I decided to do these in black. But yeah, so when you're looking at it all together, this looks to be at least a 3 or 4 layer board, just going off the color, blue, green, red, white, or yellow. So this, he probably has a ground plane in there and a number of other connections. So the more complex your board gets, the more layers you're likely to need. So kind of keeping things as simple as you can. Also, they are going to charge you per layer. 2-layer boards are dirt cheap. You can make and order your own assembled board for very little, as long as it's simple enough. When you start adding layers and complexity, that's when things start to get expensive. Throughout soldering all of these, and this is how your boards came, naked, just barely anything on them. So this is how they came. No buttons, no USB, no ESP32, no U3, no headers, no DHT22. Just the capacitors, resistors, that one USB to UART chip, and that's it. The rest is all soldering. Now, there is a component shortage going on right now, so this was made worse by that. Generally, I would not have had to solder on so much stuff, but in this case, there was a bit of a shortage, so it kind of turned into a lot. So for soldering, I'm not really going to get into it, and I don't know why, but I never even thought to record myself soldering any of these, but there's a couple of different ways I had to do this. So for the USBs, for example, sometimes that would take hot air rework, which is when I will cover the module, or at least the plastic bits, in what's called Kapton tape. This is a thermally resistive tape. It's very, very good at keeping heat out, and I'll blast the connections with extremely hot air until the solder actually melts and bonds the pins to the pad. And you can see a little bit of that here. The soldering wire would be your actual physical solder. So you would take your component, pop your your connection, right, the tail of that component through your board. You'll have a copper pad to solder to, and you'll get the pad hot. That's a big misconception about soldering, is that you want to get the components wire or line heated up, when in reality you very much want the pad heated up. So if any of y'all do get into soldering, best place to put it is actually right where it's shown here. It's right at the junction where the pad meets the component, because you want nice even heating for each connection to assure that you actually have a good connection. Throughout making these, sometimes I would solder and complete a board, plug it in, and it would not get recognized by my PCB, by my PC. Device manager had nothing to say about it, or it would just give me warnings and whatnot. So this would involve me going back in with a multimeter or something else, and testing these connections. Generally, if my computer can't see it, I can assume it's the USB connections, because those are the smallest, finest connections on there, most likely to have, had soldering mistakes when I put it on. So there was a lot of that. Yeah, I had a whole pile of them going for a little while, of just PCBs that were not being read by the computer. So that's one way of diagnosing it, but really it's, the testing's the next slide, so I'll get into that. A couple of things about soldering, though, is ventilation. For like the longest time, I was soldering with no ventilation at all. I would just try to blow the smoke away from my face, which I don't recommend any of that. Even if you get ROHS like solder, which is lead free, you generally get exposed to lead no matter what if you're soldering. So you just want to make sure to wash your hands and have some kind of fume extractor going when you're actually soldering to redirect those fumes. Even a strong enough fan will work, but you just don't want to be breathing any of that in. So testing. Once you have everything assembled, and you think you're good to go, as I just said, you'll plug it in, see if it works, right? So this was an example of one of them working. I don't have any more that are broken, so I couldn't show you an example of one that doesn't work. But just a couple of other ways to test this out. Showing this in boot mode is when IO1 is drawn low, right? So I want to take my multimeter and hook it up to those exact connections, which I can also do on the pin header. This makes it a lot easier. And if you are doing a PCB, I do recommend that you leave extra pads, or sometimes even an extra via of a larger size, something that you can probe into to actually monitor and check out what's going on if you do encounter an issue. But these are all things to kind of think about when you're actually doing the layout and the routing and actual PCB design. But this worked out just fine. The buttons were fine. The flash mode should draw that pin high. We're getting a little bit more than 3.3, but again, that's all good because it's not actually going to the power supply of the PCB. So once you're done making your model and you want to take the 3D element to it, I use Autodesk Fusion 360, and you can export your PCB as a 3-dimensional model, load it into your CAD software, and from there you can go ahead and design some stuff around that. So I'll try to do the 3D printing a little bit briefly, and I have a little video of a simple 3D printing going on. I did not do a video of the very simple case that I made for this, but there's 3 major elements to CADing this, or making a housing around it. So you'll see the mock board in here, right? The 3D model of the board. The blue that is encompassing the face of the LCD, that is my sketch plane for the very first sketch that I'm going to do for this. So you have sketches and extrudes. Sketches are 2-dimensional, extrudes are 3-dimensional. So you can draw a shape and then drag that shape forward. So I've highlighted this area because I know I'm not going to need to go beyond the face of this. I just want the actual face drawn backwards. So I can do a sketch plane here, draw this whole image with the intention of extruding it this way. So in the bottom left, you can see that I've projected the rest of these shapes. Now, a projection is just to take the physical shape and to pretty much convert it into a sketch version. So it just makes a 3D, 2D essentially. So once I was able to see everything, I made all of the sketch lines what's called construction. This means they're not going to extrude. They're just there to kind of give you a reference point to what you're actually doing. So we made a simple shape just to cut out the LCD and left room for the DHT22. So that way when we printed it, it will just fit right in and you'll just have both of them popping up. So you can also see that when I exported that, it didn't factor in the DHT22 being at the right height. So this would involve me just going back in, fixing my sketches and extrudes, and then reprinting to account for that. So actually 3D printing is not how most people think it is. A lot of people think you just get a 3D printer and print with it. There's actually a lot that goes into it. If you do get a 3D printer, I do recommend this one though. This is an Ender 3 Pro. It's what I have. It's like $270. And this is one of the very few printers that is as close to functional out of the box as they get. That said, test prints are generally very necessary, and a lot of manipulations with the settings of what's called a slicer, which is your, it's not for creating 3D models, but it's for preparing a 3D model to be 3D printed. It'll convert a 3D model into what's called an STL, which is a toolpath file, which just pretty much tells the printer step for step where the extruder or nozzle should be, how much plastic it should be pushing out, how fast it should be moving, etc. A couple of key settings though is object printability when you're designing something. So this, for example, is the face to a sensor that is another project of Dr. Fu. So when I was designing this, originally I was thinking of having it printed on this face. This didn't work because I had this guy here, which I need this here for just as a constraint for the project. So printing from this face is out. Printing from this face is out because we have this enormous overhang here. You can't print on nothing. So you've got to factor in a lot of stuff when you're designing stuff, any kind of model that is intended to be printed. Things have to be printable. You can't have crazy overhangs. Height also, if you wanted to do just something this thick and 2 feet tall, you're probably going to have a problem, because by the time the printer gets all the way up here, the little bit of plastic that's sticking it to the bed might not be enough to hold it in place when the nozzle is actually laying layers down on the top. So things can break off, and then it's a 12-hour print right out the window. So this is my slicer. Now I don't expect anybody to go and get this. It's I think $150. Most slicers are free. Plenty of them are outstanding that are free, especially for the Ender 3 Pro. Really anything will work with it. It just takes dialing in your settings. So this is just a simulation of how my printer will go about exactly printing that model, depending on what I give it for its settings. So for the layer height is essentially everything. How much detail you get is completely dependent on what your layer height is set to. So shorter layer heights, more detail, longer prints. I think I printed a very small container once that was about 1.5 inches, if that tall, but it was with a 0.2 millimeter nozzle. So the hole that the plastic was extruded from is only 0.2 millimeters in diameter. And we were printing with a layer height of, I think, 0.01 millimeters. It was like a micron per layer. So to print something 1.5 inches tall, it took like 11 hours. Now this, we're doing 0.2 millimeters. This only took about maybe 3. We're also doing it fairly slow because material is another huge consideration. There are a lot of different 3D printing materials out there. The most common is PLA. It's also the easiest to work with. It's also one of the most brittle. Well, not brittle, but it's not heat resistant really at all. So I essentially print exclusively in PETG, some kind of polyethylene plastic. It's very strong stuff. It is very thermally resistant. You could leave it out on a Florida sun on a hot day and it won't melt. PLA will turn into a puddle in a couple hours. So for PETG, we have to adapt our settings a little bit different. PLA, you can print at 180 degrees C to maybe 215. PETG, that's going to come up to about 235 degrees C to maybe even 255, depending on the printer. Some of them have offsets and whatnot. But a couple other key settings here would be the first layer width. Sometimes you want it to kind of smush the plastic as it comes down, so it'll be nice and spread out. That way you won't have a porous bed that you're printing on. The speed is also incredibly crucial. If it's going too fast, you won't be laying down enough plastic. If it's going too slow, you might be laying down too much. So a lot of this just takes a lot of fine tuning. There are a number of test prints that you can do online that'll tell you exactly what's going on with your particular printer. And I had one right up here somewhere, but it appears to be gone. It's not super important. But this is a quick time lapse of this actually printing out one of those test prints. So this is extremely sped up. This, I think, was a 3.5 hour print, and I just switched back to a 0.4 millimeter nozzle from a 0.6. So not all my settings were tip top, which is why you see stringing there. There's extra plastic being laid down. It's still printing the shape out, but it's not doing as good as it could. Whenever you switch nozzles like that, it's sort of like switching filament. You're gonna have a little bit of a dial-in phase. But yeah, generally the 3D printing is about, like, the major considerations are really just the time it's going to take, how strong you need it, and all that stuff. Yeah, that 0.2 millimeter layer height isn't bad. So this is an example of a test print. This is kind of really seeing what your printer is capable of. An overhang like this is generally pretty tricky, and you could see the longer, less neat layers from printing at such an angle. It's essentially printing over nothing very briefly. And you can see the same thing here kind of drooping down. That's called bridging, and all this takes a little bit to dial in. Once you do get it working though, you can generally just set a print up and you can trust it. You just put it on and forget it. So I know Dr. Fu is going to talk about programming a little bit, so I won't do this for too long, but once you have all of this in order, you have your PCB, everything is ready to go. You can go ahead and pick an IDE that you would like to use to manipulate it with. Boards that we have seem to work fine with Arduino IDE and the ESP IDF command. So I think I actually messed up when I was typing this in here too. Oh yeah, I can't spell to save my life, but yeah, this is, I think we already went through this in lecture 3 or something like that, but same thing. You can generally program these to do whatever you want. And just as an example, I will show y'all one of my simple or ESP32 projects. Just takes a moment. So this monstrosity is actually a wireless USB mouse that I am using with just my hand. It's just a gesture mouse. So this is the ESP connecting to the, well, via my PC. Oh, I think I clicked. But it's connecting to my PC via Bluetooth and, let's see here. Yeah, so it's connecting via Bluetooth and it's essentially just running a simple code that I wrote. So if my hand is level like this, it's not going to do anything. But the second I put it up, I'm now going to be gesturing to the computer. And, oh wait, you guys can't see the, I forgot I put it on the other screen. Yeah, so just me waving my hand around is doing the mouse. So that's a pretty simple script. It wasn't that hard to do, but there are plenty of libraries out there that can help you communicate with these. But that's just one example of what you can actually do with these devices. Somebody else made a drone. Again, to see what you can do with an ESP32, just go to Hackaday.io. People do all kinds of crazy stuff for this. Oftentimes they will give you their schematics, their codes, their documentation, and you can kind of get into this by sort of just copying what other people have done. You can pick a couple of different projects and sort of see if you can combine them together. But for the remainder of my time, I am going to show y'all how to actually design a very simple circuit, or at least the editing process of it. So I'm going to assume that we already have our schematic here. Now, I do already have a PCB for this, but just to show you how simple this can actually be. So as I think David asked earlier, this same USB connector as I used before, BCC is just the net name. I can change this to whatever I want, VDD, but I'll have to change every corresponding one as well. The pin names, you'd actually have to change in the symbol editor. But this is just a simple oscillator. You can generally find a schematic for this really anywhere. This is one of the most basic circuits out there, but you can find resources of how to actually make the schematic. But once you have the schematic, for at least easy EDA, it can be very, very simple. You just can go to convert to PCB. You can have it check the nets. I'm not going to do that for this one. I'll save that first. So from here, now we're in our PCB editor. We have a couple of components and we're going to place these guys. So since this is a USB, I want the USB face to be outward. And this is the exact same USB that is marked here. This USB 2 corresponds to USB 2. Now for an output, I just have this little connector. So I'll just pop this guy on the side here. We'll throw our main IC. Now this is another package. It's just a package type that is also affiliated with this guy. So just to show you real quick, I'm gonna take the name of this so it's easy to find, but you can go to place, symbol. Now, what I like to do is go to JLC PCB assembled. This means they will put it on for you. If you can find it in this library, they'll do it for you. So I can search that component, and I can grab this component. So also, if I'm not so specific, if I just do any 5555, it'll show me a couple of different footprints. So this is the same exact chip, more or less. They might have a couple of differences. I haven't read about the DR in the data sheet, but this is essentially the same chip with the same pinout, different package. This is a much larger package physically than the one that we have in this schematic. You can see a little bit of difference in the shape, but they'll show you in the bottom right-hand corner that it is a lot smaller. So we'll get out of that. Yeah, so paying attention to the net names, the threshold, and whenever you highlight a component, it'll show where like the net that it's connected to in white. So since this guy is going to threshold, it's kind of caught on two of them. It can't really decide, but that's close enough to the top. That's V0, so we'll pop him down here. And again, just making the silk screen readable by changing the orientation of some of these components. I'll try to do this as quick as I can. U15 to ground, yeah. So since, see this U1 underscore 5, there's no other component that's affiliated with that net. This is just simply going from this pin to this capacitor to ground. So we're just gonna leave it as is. Now you might notice I don't care about ground. And the reason is we're going to add a ground plane to this, and it will automatically connect absolutely everything that has the same net name as ground. So we don't actually have to worry about any of those ground connections. Now you can do the same thing with your voltage or your VCC, but it's entirely up to you. It's just my preference that I like to use ground up top instead of power, but it's all up to you. And make this readable, and this last guy, yeah, we'll just throw that right there. And maybe not. Sure. So one last thing, let's just get these maybe slightly more out of the way, a little bit prettier. And sometimes you'll see something like this, where you're just describing that these are both R1 and R4. It's essentially one or the other. Let's add a couple of connections. So hotkey for this is W. It's going to be different by the editor, but this is essentially drag and drop, which is why it's kind of the fun part. And again, those are no 90-degree angles, and this will actually call you on that. So if you see this last trace, how I had this little extra bit, how it's dipping down, this isn't terrible. It won't ruin your PCB, but you definitely don't want it. Luckily, this editor is easy enough.
Brandon, what are the thin lines? Those blue thin lines.
So the thin lines, these blue thin lines are your nets. That is every net. So each one has its name. So this THSH, this is your threshold. And we combined a number of these pins because they were all connected to the same net in our schematic. So we see reset, trig, and to this resistor in between VCC and ground. This all has this net name. And when we convert this to the PCB, all of these blue lines that are connected to this specific name. So if I delete this, it'll show a blue line because it's a net that is yet to be connected. This has not been connected yet. So it's simply telling me that, hey, this is a connection that you need to make the net that you designed in your schematic happen on your PCB. We'll have a couple of these guys to do. So again, no 90-degree angles. This is acceptable, if not ideal. And another thresh, which again, just trying to go kind of quick. So also V0, I'm not going to bother with any of those to connect because I'm going to add a ground plane to, oh yes, so, right. And since that is pretty ugly, we might do that a slightly different way.
So it means those thin lines, you have to collect them together, right?
Yep, every set of blue lines here, like so this V0 will have a line drawn to the nearest corresponding net. So if I disconnect this component for a sec, and you see how this blue line is going right to this V0, it's only because it's closest. If I move this over here, it'll reorient itself to be telling me to connect to this V0, just because it's proximal. So that's really what I meant by pay attention to the net names and where you want to put them. So since we have a R2_1 here, it's right next to it. That's a very easy connection. This is a limiting
because
resistor.
I was concerned that there are a lot of crossover, right?
Exactly, and that's exactly what we want to try to avoid. So initially, I'm getting everything out of the way that is not VCC or ground. Those are the only connections that I'm going to do right now, because VCC and ground will take all of 2 seconds to connect. Actually, this that looks like about the last net. Okay, so to do our VCC and ground, I'm going to do a copper area. And you'll see here that this is blacked out. That's because I'm switching from the top layer to the bottom layer. So now if I go and do another route, it's gonna show up in blue because it's on the bottom layer. Now, if it's a through hole like this, you can connect directly to a through hole component because there's copper on both sides of the board. But since these components here are SMD, this is not connected. This is on a completely separate layer than this ground connection. So to do our power connections, we're going to first increase the width of our traces to 0.45. I mean, this is a pretty small amount of energy, so we're okay. But I'll bridge these two just because they're proximal, and I'm gonna add a via right in the middle. Now, this via is gonna just connect this whole net here, this entire connection. It's gonna connect that directly to the bottom of the PCB. Now, there's nothing down there yet. I haven't added in a plane, but it will be a means of connecting both. Again, we had kind of skewed lines. So our power is gonna come from the bottom side of the PCB, and that's really just what's important here. And this will also give your PCBs a lot better of a look as well. And you see, I don't even need to connect these. They're, oh wait, that's V0. Yes, let's be careful with this. So we need VCC. So there are two powers here. There is VCC and V0. So let's take care of the ground plane for VCC first. So first thing, when I hit copper area, it's going to ask me for a net. It wants to know which connection I'm trying to make contact with. So since I am trying to connect to VCC here, I'm just going to hit OK. And I'm going to just start drawing this out. Now, somewhere I might want to avoid is the V0, because then there's no VCC over there. Let's actually undo that. Yep. So looking at where the lines are, so this is V0. I don't even need to go as far as that. I can stop this copper trace or this copper plane right here and then continue down, find my VCC here, encompass the via, encompass the other via. And what I can also do is just come right back the way I just came in. And what this will do is this gives me room to add a other, like a secondary under plane, like a secondary plane underneath that can affiliate V0 if I did not want to connect all those copper traces. And just like that. So see how this just filled in all solid, and now if I go up here, it's not telling me these lines are here anymore. So these two are now connected because they're going through this entire flat copper region. So if I take this from a solid to being non-solid, now they're going to complain about how they need to be connected again. So, and also while you're actually doing the PCB, it's generally good practice to just leave that kind of thing off. So for V0, we can, what width are we on? Yep, we're still on a good width. we'll take a large trace and we'll just come down and pop it right about here, place a via, and we're going to do the same thing. We're going to go V0. Oh, wait, that's on the top plane. Oh, that's in red. We don't want that. V0. And we can kind of just follow the same traces that we did for the other one. Can be a little bit hard to see when the other one's not in solid mode, but yep, that's actually just about all we would need. We'll try to make that a little bit prettier. So there we go. This connects all of our V0s. And since this one is not connected, we can simply drag that over. Now, generally, oh yes, that's on a copper trace, that's why. So let's go back to the top layer, get rid of that, remount it, pop that V in. And then from there, we can also just kind of connect it if it's nice and easy up top. So apart from that, if I also add in the solid here, every VCC is connected. So I kind of went with where my connections were. And there's only one more copper layer to add, and that's going to be the ground layer. I'm going to do this right up top. And I can just essentially outline the entire board. This does not need to be a particular shape because I'm not going to put any other voltage or anything up top. So this is, as of right now, this will work. We can order this as is, and this will work. But if we wanted to make things a little bit prettier, we can add a couple more vias, and this time we're going to make these enormous. That way, let's do a 2.5 millimeter hole with a 3.5 diameter button, and copy this, move this down here. And on top of that, we can add in text if you want, throw your name. Now this will go on the top later. And I could just say like UMass or something. And then you can dictate the height, say 1.5 millimeters, something like that. Just make it a little bit more encompassing. So if you see here, actually, can anybody note what's wrong with this? What's wrong with exactly what I just did? I just want to see if you guys are paying attention to your colors. Nobody? UMass is in red. So keeping in mind the layers of this, looking at all these layers, what material will that UMass come out as? It's going to be copper. It's not going to be just printed on there. It's going to be an actual copper conductive trace. So we don't want that. So to fix that, I can just right click it, go to attributes, layer, and top silk layer. Okay. Now it's just going to show up as a little bit of writing on there. We will re-enable our ground. And now we can save this guy, and we'll take a look at what it would look like once we order it. And this is absolutely everything. So we have two through hole components. Here we see our ground, or our both of our power planes. The through hole, so you would actually likely solder this yourself. Sometimes they'll put it on. Generally, if it shows up in this preview, they'll put it on for you. But we just left a couple of holes for, you know, maybe screwing this into something, or if it gets mounted on another module, because this is going to be entirely flat. But you can order this, plug it in, and if you measure this at the output, you're going to get a square wave, pretty even square wave. So yeah, to actually order this, and I think it's my other one prettier, maybe a little bit, but to order this guy, we can go to fabrication. First off, we're going to need the BOM. Now, I vetted this before actually doing this. So each of these little check marks, this verifies that, yes, we know where to get that component. We can grab that for you. It won't be a problem. So we can export this BOM. I'm just gonna throw it in downloads for now. Let's go. There we go. And for the second file, fabrication, pick and place. This is going to be, you don't want to mirror your components. I don't know why it asks that. So pick and place is going to describe every pad. And when I say pad, I mean these little guys with these net names on them. Each one of those is a pad. Those connect to each trace. These are your traces. So those are all traces. These are all pads. So the pick and place file isn't for the traces. Those are just for the actual copper pads that even they are going to solder onto. So then the Gerber files. So yeah, sometimes it's good to check the DRC. I know that this is going to complain about the USB connector. It doesn't think that you can do this. You can. And the only reason it's because this hole right here is not connected to ground. You see how the ground and the bottom stop around this hole. It's not going to bridge anything. It's not going to connect anything else. It's simply complaining that because it just does. But actually, real quick, let me just show you what will happen if I break this. So if I actually, let's do it slightly less explicit. We'll go from here to there. There we go. Perfect. Nice and broken. So now if I go to, I'll still make this solid, so it'll still think I'm doing everything okay. And I'll go to Gerber. Oh yeah, sure, save it. Now if I check the DRC, now I got these 3 errors, and it's going to complain about those 2 and this. It's going to say that this is not okay. You're going to have some element of capacitance here. We cannot guarantee that this works the way you have it. So it's generally good to at least check those out. And let's see, just solid. Oh, come on. All right, just drop this back down manually. So also the solid, the plane that we have here, we have to disable that if we change something. And it's just because it's going to recalculate it every single time it enables it. So if you do want to change any of these traces, you're going to need to turn that off, change your trace, and then turn it back on to assure that it still works. Now, if we do our Gerber, always forget to save. Yes, we want to check DRC. Perfect. It's back to the same 2 errors that we don't care about. And we can generate these Gerbers. So once I've downloaded that Gerber, I actually go right back to fabrication Gerber. And from here, I can just order this and it'll pretty much give me a quote right away. So the dimensions were really small. I mean, you don't really need to dictate what you need there because you're going to add your Gerber to this. So I'm just going to upload this entire zip. What? Did you not download me a zip? Maybe it's not done download. Yeah. Yeah, okay, that's a zip. Oh, yes. So add our Gerber. Okay, there it is. Maybe we just didn't like the name I gave it. Actually, yeah, let's see. So just while that's fabricating, I'm just going to do these with the stock names just so we don't encounter any problems. This is actually a software. It's why I pick to, or it's why I chose to show you guys this specific software, is it does so much of this for you that you don't generally need to mess with anything. There are plenty of other editors that when you actually go to order, it's going to be, you'll have to open those files, the BOM and the pick and place, and edit them yourself. And you'll have to kind of go in and figure out what your pads are, what you need to actually change. So once we're in here, we can really change some stuff around. I like to order mine in black. Here we have the actual thickness. 1.6 is standard. This is just in millimeters. We can go thinner for something that small and innocuous. You could absolutely go thinner. Sometimes we don't want to skimp on the solder, so we can do lead-free solder. And this is the option that you really want, and that is assembly. I already chose for, oh. Yeah. Okay, great. Oh, I see. It needs to be 20 by 20 for them to assemble it. Oh, that's actually not a problem. We can actually just go to redefine board outline, and yeah, we can set that fairly large. Why are you in mils? I hate mils. So yes, set board outline. They need 20 by 20 in order to assemble it, or 20 by 23 then I guess we'll do. Yeah, sure, 25 by 25. So this will look a little funnier, but whatever, it'll work. That does mean re-downloading the BOM though. Yep. And re-downloading the pick and place. But believe it or not, this is actually so much less of a pain to order through these guys than to go through somewhere else. There we go. All right, let's try this again. So we'll add the Gerber. This always takes kind of a minute to go through. It's got to process at least 6 layers in there. So yeah, this looks really goofy, but it's just because we resized it so they'll actually do it for us. So go to PCB assembly. Now it's saying, which side do you want assembled? They will only assemble one side for you. So if you do put any components on the other side of your board, I would make sure they are components that you are okay with soldering yourself. You generally don't need to. You can have a pretty extensive board that is completely one-sided, and it's generally fine. All right, so now we'll add our BOM and our pick and place. We'll hit next, and we'll be able to see how cheap 5 of these are eventually. But still, this is probably the absolutely easiest way to actually go from a concept to a full PCB, especially with the ordering process. I'm telling y'all, you'll have to go in and set it up a completely different way. I've had editors give me BOMs that have had to be completely restructured, move around columns and whatnot, just to get the ordering, or the company I'm ordering from, to be able to read it and see it, verify it, and actually eventually use it. So this is the easiest way that I have found to actually get a PCB made. And again, you don't even need to download this software. You can do all of this on EasyEDA's website.
How much was our PCB, one piece?
These guys, it was 170 for 25 of them. So like $9 or something.
Okay.
Not much.
Okay. But we want to actually make sure everything goes to one, actually $10, right? That means we have to go to China to print everything, right?
Definitely, yeah. If we got this, even this board made in America, we're probably, yeah, we're paying, $5 a board. Whereas if we order from China, we're probably paying like $2 for, like 10 of them. I don't know why this is taking so long. This usually doesn't. My internet's kind of been weird today, but these are generally very, very inexpensive to even have them assemble it for you. The most expensive board I've actually done is, or not the most expensive, but most expensive recent board is actually the kind of the next iteration for the board in this class, and that would be this fun little guy here. So not everything's even turned on. to be enable that enormous ground plane. So now it's just has to calculate everything just to populate that plane, add in all of these connections. And it's got to do a lot of work because I put all of my components on the top except for these two ICs. So this guy is a lot more extensive. And if we look at it in a 3D view, they will assemble this. This wasn't actually too bad either. It's mostly this chip U1 here. It's like a $6 chip. So it's just more expensive because they're going to charge you for the components and for the placement and tooling of it and actually soldering of it. So yeah, just to show you a little bit more of a complex board. These guys, for 5 of them, I think it was like $70, which was a good step up from 5 of my last one. So yeah, just the price is going to go up with complexity. And again, the parts are going to be really important. Like these two are pretty affordable, which is again why I put these guys on the back, is because I'll have no trouble soldering something with pads this size. Whereas all of these tiny little components, like these are under 1 millimeter long. So yeah, expensive parts are what's going to really drive your price up. It's not by the part count. They won't charge you much. If I just got rid of this one chip, it would cut the whole thing down by a ton. So how much you want to pay is really just indicative of how important the project is to you. But it's not absolutely everything, but it's concept to PCB. I mean, do we have any questions?
Any questions? Let me see, what is time now? Okay. So Brandon, are you done?
Yeah, unless people have some questions, let's say we're good.
Okay. So let's rest. I want to finish the next part, and the next part will be short. And so I want to finish next part about how to use the I/O. Okay. And so let's rest 10 minutes. Then we'll come back at 5:40, and I think we can finish it. And so we come back at 5:40. Then we'll finish the next part about the I/O. Then you guys can actually do your next assignment. Okay, I know the assignment 2 is not due yet, but I just want to give you assignment 3. That is 1 week after the second assignment. Okay, so let's come back at 5:40.
Sounds good.